film all of this then, so please make a start.
Okay, thank you.
And ignore the guy in the corner.
Thank you for the invitation. So we're a small group, so feel free to interrupt anytime something's unclear. So this is joint work with Angus Davidson, who's a PhD student jointly supervised by Balint, Toth, and myself. Okay, so let me start by telling you what the problem is in case any of the words in the title aren't familiar. So in general, the Steiner tree problem is you're given some number of points on a metric space, k points, and you want to connect all these up at by a tree of minimum total weight or total length. The point is that you can use intermediate points in the metric space to connect them up. So you're not just adding up the shortest paths between these points, let's say. And in our case, the metric space is going to come from a graph with weights on the edges. And this problem is known to be difficult in the usual sense, unless you are connecting all the points on the graph, in which case the Steiner tree connecting all of them is the minimum spanning tree, and that problem is very easy to solve. There's a linear time algorithm for that, which is the greedy algorithm. So we are going to look at this not on a fixed graph with fixed edge weights, but on a random metric space, so random weights on the edges, and look at what the weight of this Steiner tree looks like, how it behaves. So the model we are going to look at is a complete graph on n vertices, so there's an edge between every pair of nodes. And the weights on all the edges are independent, exponential with mean 1. Okay. We'll use this exponential assumption very strongly, but it's not an important assumption for the results, as will become clear. What's important is the weight, is the density of the distribution at the origin. So the density near 0 should be 1, and then all the results go through. But it's much easier to reason about how we do things if we work with exponential. Okay, so again, the problem is the following. We have a graph on n nodes, and we fix k points on the graph. And the way we are going to think about this is k is a fixed number and n is going to infinity. You could also look at both going to infinity in some related way, but that's not what we do today. K is fixed. And we want to find the minimum weight tree connecting all these points. And there are two kinds of objects we are going to look at. So you have k typical nodes, in which case we'll call this wk. And then we study asymptotics, as I mentioned. But also we look at the, okay, so first let me tell you about some prior work on this. So this problem was studied by Bollobas et al. And what they showed is that, so if you look at the weight of this random tree, the sum of the weights of all the edges on the tree, then it scales as follows. It looks like k minus 1 times log n over n roughly. So they were looking at joint asymptotics in k and n, where k just has to grow slower than n, so they kept both the terms. But for today's talk, k is fixed, so the log k term is negligible compared to the log n term. So the version of their result that matters to us is this one. So it grows like k minus 1 log n over n. And this is for the model where you can think of it as either you fix the k nodes in advance and then you realize the random edge weights, or you first realize the random edge weights and then pick the k nodes uniformly at random. So that's one version of the problem. And the other version is that you realize the edge weights and then an adversary comes along and gives you k vertices. And in that case, how big is the weight of this Steiner tree if you've chosen the worst k vertices for this problem? And we'll call this m sub k for the maximum. Okay, so the special case of k equals 2, if you fix two nodes, then this is just, you're just asking for the shortest path between them. And you can ask what's the typical shortest path or what's the worst case shortest path between the two furthest edges in the random graph. And these two problems were looked at by Svante, who showed that in the typical case it's log n over n, and in the worst case it's 3 log n over n. So similarly, we want to do the worst case for the k-Steiner tree. Okay, and so I'll use the tilde notation a lot just because it's lighter, but there's a more precise statement of all these results. So what you're saying is that if you scale these random variables by log n over n, they converge in probability to these deterministic limits. You can also ask about fluctuations. In the case of two nodes, so for the shortest path, you have a characterization. So on first order, the typical behavior is that suitably scaled, it converges to 1. So if you multiply by n, it should be around log n. If you look at the fluctuations around log n, they are of order 1 in probability, and you can write them explicitly in terms of 3 independent standard Gumbel random variables in this way. So this again due to Janson. So there's a very nice characterization of these random variables, both the mean and the typical behavior and the fluctuations. Okay, so those are the kinds of questions we are going to ask about Steiner trees, but before that, there are a number of other problems in this framework that are interesting. So this random edge weight model has been used to study a number of different combinatorial optimization problems. And this is what's called the stochastic mean field distance model in the title. One example is the minimum spanning tree, which was studied by Fries, who showed that for n nodes complete graph, the total weight of the minimum spanning tree is zeta of 3. This is the Riemann zeta function at 3, so it's the sum of this infinite series. Other problems, you can also look at the shortest path tree. So you fix one node and you look at all the shortest paths to all the other nodes. So you run Dijkstra's algorithm on this graph and you get a tree which is the union of those shortest paths, and you look at the sum of the edge weights on that tree. And if you do that, it turns out that you get zeta of 1, and this was shown by these authors. You can also ask for the traveling salesman tour. So Alan Fries again looked at this and showed that it's bounded between the minimum spanning tree, which gives you the zeta of 3, and another constant, which I think he got by looking at a version of when a directed, I think he looked at 2 in, 2 out random graphs. So each vertex has 2 edges coming in and 2 edges going out, and this is connected with high probability. So if you retain only the minimum weight edges, you get a connected graph, and you can find a traveling salesman tour on this graph with only these low weight edges, and so you should get an upper bound on the TSP. In fact, this problem was also interesting to physicists, the traveling salesman problem. And this was work of Mézard and Parisi in the 80s. So based on some symmetry arguments, well, some quite statistical physics arguments, they came up with solutions for a number of random combinatorial optimization problems. They were not rigorous in the mathematical sense, but They solved a number of hard problems, and it turned out that their answers were all correct. So it took another 20 odd years for Bristol to show rigorously that indeed what they said was correct, and this way converges to a constant which you can explicitly write as an integral of something. Okay, so coming back to the shortest path problem. So I mentioned already, so you can, if you look at the worst case pair of nodes and the distance between them, you can call that, it makes sense to call that the diameter of the graph. So the typical behavior of the diameter was 3 log n over n, but what are the fluctuations around that? That was studied by Bamidi and van der Hofstadt, and they gave an expression for that. Okay, so that's some background about this problem. I'll say a bit about our results. So what we show is we look at the worst case k-Steiner tree, and we show that the total weight of this is not k minus 1 log n over n, but 2k minus 1 log n over n. So in the particular case that k equals 2, this gives us 3 log n over n, which recovers Janson's result. Okay, and a bit about how we go about proving this. So as with previous work, it relies on studying first passage percolation on this graph. So what you do is you think of an infection spreading on it. You start from one single node initially infected, and the edge weights encode the time it takes for the infection to pass along an edge. So there's a random edge weight. It tells you if one end is infected, how long it takes for it to infect the other end. And then the shortest path length between two nodes is just you start the infection at U and ask at what time did V become infected. That's the length of the shortest path between U and V. So once the node is infected, it remains infected forever. And now there's a very simple analysis of how this spreads. So let's not think about specific nodes yet. We start with one infected node and just count how many other nodes are infected up to some time. So let's denote Tk, the random time that k nodes are infected for the first time. Well, at this time Tk, there are k infected nodes, n minus k susceptible nodes, and this many edges between them. And on each of these edges, there is an exponential one weight independent of the others. Now, some of these edges you might have seen already. So by the time, so let's say k is 10, so 10 nodes are infected. At the time that the 7th node became infected, you've seen a lot of edges from the 7th node to other nodes. But what do you know about these edges? You know that until the 10th node became infected, no infection passed along these edges. And now we use the memoryless property of the exponential to say the excess time until you pass infection along any of these edges is still the exponential one. And this is where the exponential assumption is really useful. So the time to infect one more node is just the minimum of this many independent exponential random variables, which is exponential with parameter k times n minus k. So you can write down its mean, and you can, if you want, write down variance, moment generating functions. You can do all your calculations using this representation as sums of independent exponentials. Okay, so that's the key step. So you could, for instance, ask how long does it take to infect all the nodes? Then you just add up these random variables. The expectation is the sum of the expectations. It gives you 2 log n over n. And why is the typical edge length log n over n? That's because you've picked your nodes at random, so if you start your infection at U, at what point did V become infected, it's equally likely to be anywhere between nodes 2 through N which got infected. So you're picking something uniformly between them, and that gives you the log N over N. You can also look at the time course of the infection. And this might be useful later. So
It's automatic. It always disturbs me when it happens.
oh, it's automatic. So if you look at time and number of infected nodes, then what you see is that you start from 1, you go up to N, but there's a sharp transition at log N over N. So initially there are very few nodes infected. And around time log N over N, it goes from a fraction 0 of infected nodes to a fraction 1, basically. So initially you're infecting a very small proportion of the nodes, and then you are picking up the last few nodes to infect later on. And again, that will be useful for us. Okay. Okay, so where does the intuition for our result come from? So as already mentioned, the typical distance between pairs of nodes is about log N over N. But again, we use the intuition from Svante's work. The reason that if you're looking at shortest paths, you get 3 log N over N is that there are some nodes, out of N nodes, there's a small number which are very far from everybody else. So the nearest neighbor distance is already log N over N. For a typical node, the closest neighbor is at 1 over N. It's the minimum of N exponentials. Whereas for some of these badly behaved nodes, it's log N over N instead of 1 over N. And so you can pick these remote nodes. So the structure of your graph looks like this. You have a dense core where the distance between any two vertices is log N over N. And then there are things out here which are log N over N away from anybody. And so the point is that you maximize the distance by picking 2 of these nodes in the periphery, and then the total distance is log N over N to enter the core, log N over N to connect to the other neighbor in the core, and another log N over N to go there. And it's the same if there are k nodes. So you have to pay a penalty of log N over N, k times for each of these to get to the node, and then you are in the typical setting, you connect up the k nodes in the core with a Steiner tree as given by Bollobas' result of k minus 1 log N over N, and then you're done. Okay, so this intuitive reasoning gives us one direction. It gives us a lower bound on the weight of the minimum Steiner tree. Is there, okay, so this tells us that there's one way to be bad, but is there, yeah, could you possibly be worse than this? So we also need an upper bound, so the intuition can be turned into a lower bound. This is just what I described. Can we get an upper bound? So I'll mention two loose upper bounds and then how we get there. Well, very sloppily you could say you're given k nodes, just connect, find shortest paths from one of them to all the remaining k minus 1. Even in the worst case, your shortest paths are at most 3 log n over n times k minus 1 is an upper bound. You could do a bit better. You could say, let's start from, you're given k nodes, pick something else, pick some other node uniformly at random, and start spreading the infection from there. You know that started from a typical node, the infection is going to reach everybody in 2 log n over n time. So find the paths along which the infection traveled to your k nodes and take the union of those paths. That gives you k times 2 log n over n, which is almost there. So it's not quite 2k minus 1. So it took us some hard work to get that little bit extra. Yeah, so how did we do that? So, okay, so we have to work a bit harder. So we find a construction that dominates the weight of, not of the worst case k-Steiner tree, but the typical k-Steiner tree. And then we bound the tail of that random variable. We find a Chernoff bound saying that this typical k-Steiner tree cannot be too big in weight. And then we apply a union bound. So there are n to the k ways of choosing k nodes. So if your tail bounds are decaying sufficiently rapidly, then you can add up n to the k of these and still it will decay. It will vanish. Okay, so that's the idea. So I won't obviously go through the calculations, but tell you how we construct this dominating object. So what we are going to do is give an algorithm to explicitly construct a tree, which is good, maybe not the best. And then we'll say what's the weight of the tree our algorithm constructs, which is an upper bound on the Steiner tree. Okay, and the algorithm is the following. So now we are in the typical setting. So we pick k nodes, and you start k different infections. So k colors, each of which is spreading from each of them. And you grow these infected sets until you reach n to some fractional power of nodes. So there's a red infection, a blue infection, and a green. Each has grown to n to the 2/3 nodes. Okay. And if you do this, then all these 3 subsets will have a node in common. So this is just a generalization of the birthday paradox. If there were 2 colors, you grow each to square root n and you have something in common. If you want 3 sets to have something in common, you have to grow to n to the 2/3 and for k, this many. So the idea is simple. Slight difficulty is that these sets are not quite independent. If you were independently picking subsets of this size from the vertex set, then you're done by the birthday paradox. The independence breaks down because as you are growing these sets, they might meet. Before all k have met, 2 of them have met, and already you have dependence. Okay, so we have to mess around a bit to get around that. So if you, so what we want is to grow them big enough that all 3 intersect, but as soon as 2 intersect, they are dependent. So what we do is we grow them not quite to that size, we grow them a little smaller till they have not intersected. And then, so then we come to this intuition here of exponential growth. So throughout this first phase, though it looks like a sharp transition, there's exponential growth here. So we have grown up to n to the 2/3, let's say, or n to a little bit 2/3 minus epsilon. We are here. There's exponential growth, so what we are going to do is look at annuli around these sets we have grown, which consist of a single hop. So not paths, but just looking at if you only move to your nearby neighbors, how far can you get? So we grow it a little while longer, and by construction, these annuli are independent because they are looking at different edges. And because it's exponential growth, in a little bit more time, in epsilon more time, they would have grown proportional to their size. So it's epsilon n to the 2/3 to n to the 2/3 doesn't take you much longer to grow that. So that's the idea. Okay, so you grow these sets a little smaller than you need, look at one hop neighbors, grow an annulus around it to get up to n to the 2/3. These annuli are independent and they intersect, and it doesn't take you much longer to grow these extra annuli. Okay, so that's, so that gives us an upper bound matching the lower bound, so that gives us the proof of our result for the k-Steiner tree. So it's easier to draw for 3, but same idea for k. Okay, so this was our first result. And then, so we had this result, and then Balint asked us this question, which is, okay, so what's the shape of this random tree you have constructed? Is it always the same? Is it random? So the way we so our bounding algorithm by definition constructs things which are all the same size. So if you want to connect these 3 vertices, it creates this star where all the path lengths are roughly the same. But is this in fact the shape of the Steiner tree, or is it quite different from that? Now, okay, so we did this for the worst case, but you can also do this in the typical case, and for the shape, I'm going to talk about the typical case. So you can, again, do the same. This construction was for the typical case, which was used to bound the worst case. And so the weight that this typically gives is the total weight is 2 log n over n for a 3 Steiner tree, and each of these is 2/3 log n over n. Okay. But is that the only way to get this Steiner tree? If you look at the shortest paths from V1 to V2 and V1 to V3, those are each typically log n over n. So the sum is again 2 log n over n, which is the same as this. So maybe the shape is a degenerate tree, just shortest paths from one of them to the other 2. So which of these is really the case? And we can't answer this at this level because the first order behavior isn't sharp enough to answer this. They are all equal to first order. So to answer that, we have to look at fluctuations. Okay, so we don't have an answer for the shape, but that motivated us looking at fluctuations of this. Okay. So there are different ways of reasoning can give you different shapes for the limiting tree, and each of them has them up to first order the same way. That's, I already said that. So let's look at, so let's look at fluctuations. So we started out by simulating the Steiner tree and looking at the shape of it. So what did we do? So we looked at, we are plotting here the lengths of 2 of the legs. All 3 add up to the same constant, which after scaling is 1. So if you know 2 of the lengths, you know the third. And okay, if the theorem is true, then everything should lie within this purple shaded triangle.
If the theorem is true, if what is true?
So if the theorem about the weight, the sum of the weights adding to 2 log n over n is true, okay, so which it is, but that's asymptotic. For finite n, it doesn't have to be true. So in the asymptotic regime, everything should lie within this triangle for a few thousand vertices. Most of them do, but not quite. 100,000 vertices, lot better. Million vertices, more or less the same. It's very slow convergence, but you are getting there. But maybe simulation doesn't quite answer whether things are at one of the corners, which is the degenerate shapes, or the centroid here, which is all three legs equal. But it looks very much like no single shape dominates. The limiting shape is random, and it can lie anywhere within this triangle. That's what the simulations suggest.
That picture doesn't.
Doesn't
I
it?
think you'd reject the null hypothesis that conditional on being in that triangle that it's uniform. I mean, it's close, but
No, maybe not uniform, but
Oh.
that there's a distribution on it. That it's
okay,
not
but the support is
degenerate.
the entire triangle. Okay.
Yeah, it's the entire.
Thank you.
That it's not near any of the corners. Okay, so we also looked at the distribution of the weight of the longest leg, I think, or one of them. I'm not sure which. Okay, so here we right. So we looked at how the fluctuations look in the shortest path problem. So for the shortest path, the typical length should be log n plus these Campbell's minus a third. And this is our histogram for the shortest path. And one of these is the asymptotic result. The mean lies close to it. But even with, I think this was on 1 million nodes, but even so, there's quite a spread around it. It's not quite converged yet. And we did the same for our k-Steiner tree, and we found that there's a big gap between the theoretical result of 2 log n over n and the average from our simulations. And so that made us, okay, so in fact, what we were trying to do was to prove a result similar to this, so to show that the fluctuations for the Steiner tree are of order 1, and we were not making progress on this. And I gave a talk at a workshop in Eindhoven last year, and Remco suggested that maybe the fluctuations are bigger. His intuition was the fluctuations are bigger, they are not order 1. So then we did some simulations, and maybe the fluctuations are bigger. So rather than trying to prove order 1 fluctuations, we went back to think again about what should we be trying to prove here. And here are more simulation results which show that the fluctuations seem to gradually increase with n. Okay, and then based on some heuristic arguments, we conjectured that in fact the fluctuations should be, okay, so Remco suggested it should be decreasing to minus infinity because there are, the main intuitive reason is that in a path there are not too many choices over how you optimize. Well, all the internal nodes on the path are splitting it. There's equality for the, okay, so somehow there are not that many choices over which you are optimizing in a path. Whereas in a Steiner tree, you have a lot more choice of these internal branching nodes over which you optimize. And because you're minimizing over a bigger set, you can expect to get a smaller minimum. And that very loosely suggests you might get bigger fluctuations from typical behavior. So compared to the result for the path, where the fluctuations are order 1, you expect something growing as n goes to infinity, but how fast does it grow? And so
this is for fixed k.
This is for fixed k. This is all for fixed k. And so our conjecture is that it grows like k minus 1 log n around the log n. Okay? And what we've been able to prove is upper and lower bounds of order log n. So that's why I've written this approximately equal. In fact, Bollobas et al. Already gave a lower bound of 2 times k minus 1 log n. We got an upper bound which was something else times log n. We think this is the correct answer, but we don't know. So there's still some sharpening of the bounds to do.
But what, if you put k equals 2 in that
K
line?
equals 2 doesn't work. So k equals 2 is different. So this is for k bigger than 2, but still not growing with n, but a constant. Yeah, so for k equals 2, it's not, you're right, it's not 1 log n, it's just order 1. So maybe this is wrong, but it's somewhere between 2 times k minus 1 and some other number times log n. Okay. Yeah,
Because
so-
your intuition story made me think that while it might run off to minus infinity as k increases, it might not go all the way to minus infinity for a larger fixed k. And this way, the way I understood your story for intuition, but
Yeah, I'll give a bit more intuition, but even for fixed k, there are,
it makes, okay.
it makes,
I believe
there's some intuitive, there's some loose reasoning for why you get log n fluctuations. And then you can, making that rigorous is harder, but you can loosely argue.
If you were a physicist, you'd be done.
Remember, we're getting recorded, Carrie.
Yeah, but also knowing what constant times log n is not clear. Okay, so so I can say a bit about, do I say anything about, no, that's the fluctuations. Yeah, so I can say a little bit about the intuition behind it. Okay, let's do that. So let's do k equals 3 because it's easiest to think of that. So you want to connect up these 3 vertices with a Steiner tree. So the shape is always going to be some kind of triangle. It could be degenerate. The branch point could be one of their vertices, but otherwise it looks like this. There's some branching vertex x. So let's look at dxv1, dxv2. So we can think of an infection starting at x, and what's the sum of the times at which it infects v1, v2, and v3.
Right, and now that whole story so far holds is how you'd start if you had 2, if k is 2.
Yeah.
So remind me when you jump from the 2 to 3, because that's
Okay.
what I'm after.
Yeah, so, but we are just starting one infection
Right.
here for now, starting from some x, and we are asking, well, the weight of the Steiner tree is the sum of the times at which these 3 vertices got infected. Okay, so this is going to be so V1 might have been, so let's order the vertices that x infects. So you start with one vertex infected, that's x itself. Okay. Then it infects a second vertex, an nth vertex, and somewhere here at random positions n1, n2, n3 are when it infected these vertices, maybe v2, v3, v1, and this order. And we can look at the time at which it infected the N1 vertex. That's going to be roughly log, is that correct? Yeah, I think this is correct, log. It's log n.
Log n over.
Yeah, no, I'm just, it might not
Okay.
be quite right. So it takes, so we go back to this graph. So the time to pick up the kth vertex, so let me write the intermediate step. So this is going to be the sum I equals 1 to n1 of these 1 over I times n minus I plus the same for n2 and n3. And this gives us
But now you
Yeah.
look at three disjoint parts. Now you don't simply don't you?
yeah, I look at the disjoint parts. That's why you are looking at the sum of the times
Yes,
for
exactly.
these things to happen.
Exactly, but that will give you a little bit too much, doesn't it? So
It gives you a bit too
Yes.
much. But the point is, so it gives you a log n over n for each of them. But okay, I can't remember the steps now. But it gives you this minus 3 random variables, which are each. These are exponential 1 random variables, and this comes from the randomness in n1, from n2 and n3. So you have for the typical behavior log n over n, but you have not looked all the way to the end. You are stopping a bit sooner by a random amount. The random amount you're stopping sooner is uniform. You're uniformly picking between 1 and n. But somehow you're taking a logarithm of that uniform, and that gives you the exponential because of the exponential growth. I don't remember the detailed calculations, but this result is correct. So you get 3 log n over n minus the sum of these 3 exponential 1 random variables. Things are not quite independent, but let's pretend they are independent. We can work those out. So this is for one choice of x. It looks already bad. Instead of 2 log n over n, you have 3 log n over n. But now you're minimizing over n different choices of x. And that minimization gives you a little bit more than a log n over n term.
Good question.
Yeah.
So we know that the sums, so you're actually subtracting 3 order 1 random variables, you're aggregating distances, you'll get something negative. That can't be right.
Sorry, this is all divided by n.
Okay.
Yeah, thank you. Yeah. Okay.
That's a pretty good job actually on your part.
Okay, so to be able to subtract a lot, you need the sum of 3 exponentials to be big, and you're maximizing over n choices of these intermediate nodes, and this gives you that the biggest excursion you can get is log n plus 2 log n in this case. Okay. So you can work this out explicitly. And so that gives you, when you subtract it off, 2 log n minus 2 log n as the way, by this way of constructing it. Okay, there are additional terms which I have ignored here. I've taken the randomness coming from these n1, n2, n3 into account, but there's also randomness in the exponentials. You have to take that into account as well, and that could add additional log n terms.
Okay, so that's great. Her question was not stupid. She was right. My question is stupid. So that's fine, but I don't see why that argument doesn't hold for k equals 2.
Okay.
Because the picture is almost the same and everything you said is almost the same. Except there's only 2 instead of 3. So
I think
I am having a problem with this 2 not being a...
Okay, so I think the issue, yeah, it's a good question. The issue, I think, is that with the 3, I loosely said, well, for different choices of x, these are not quite independent of each other, but let's pretend they are independent.
Right.
And that pretending is okay when there are 3, because the paths are sufficiently disjoint. When there are 2, there's a path here, you're achieving the minimum for, you're achieving the minimum everywhere here, and for all those choices, they are extremely dependent. Whether you pick this one or this one, the sums are exactly the same.
That's good, thank you. I appreciate your tolerance with me, and that makes me feel better, because if it's an issue of how independent things are, I don't feel bad for not seeing it. Because dependence is a terrible thing. Good, thank you.
Okay.
So that's what it comes down to, though, the 2
Yeah.
versus 3, is that this dependence story is the same for k greater than or equal to 3, but...
Yeah, at least that's for a, yeah.
Yep, good.
The intuition behind it, and
I
then
like
the proof itself is quite messy.
Yeah.
Okay, so we do something similar to this construction we had earlier, where we were growing these balls, growing infections from each of them. Now the point is that...
On the other hand, sorry.
that's good.
You're not gonna get the last word with
On
Karen.
the other hand, that intuition might argue that there's a k big enough but less than n, where the dependence gets even enough worse that something else happens.
Yeah.
So
You're
whether-
having k bigger than root n or something?
Yeah, something like that. So whether this holds for all, your conjecture holds for all k bigger than or equal to 3, or just for all k bigger than or equal to 3 up to some thing where it changes again, your intuition argument, as I understand it,
Yeah, a lot more
kind of
changes.
says that might happen.
Yeah, you can't push k all the way to n.
Okay,
Even for the...
Good.
I mean, you have to
Yeah.
look at the formula.
Right, I know, you wouldn't get the formula. So there's some biggest k
Yeah.
for which this conjecture, you're gonna quit
Yeah,
giving,
it's-
okay,
yeah.
thank you, I'm happy again.
Okay, and for the proofs, we did something similar to these growing infections story. But the point is that earlier we would grow each of them to n to the 2/3, let's say, and that doesn't give you this larger fluctuation. So what you have to do is simultaneously explore lots of different ways of, okay, so maybe let me again start with the birthday paradox. So you could start at these 3 vertices and grow balls that contain n to the alpha, n to the beta, and n to the gamma vertices. And then if alpha plus beta plus gamma is bigger or equal to 1, then they have an ordered common. So it doesn't have to be 2/3, 2/3, 2/3, it could be other things. And somehow the fluctuation comes out of the fact that you're taking the minimum over all these possibilities, whereas our algorithm picks one of them. So
I like that.
what we try to do is grow things at different sizes, and for each of them explore whether something is common. And the hard part is getting a dependence in this, because it's going to be highly dependent. So what we do is we first split the vertex set into two, grow on one set, grow the annuli on the other set. And every time we look for one combination of alpha, beta, gamma to see if they've intersected, and we fail, we throw away the set we've looked at, so there's no dependence when we look at the next one, and so on. So it's a bit
That's
messy.
helpful.
It's messy, but that gives us a bound. And maybe it's that mess makes it sloppy, so we can't get matching bounds. Okay, so that's all I wanted to say, and
Thank you, Danny.
thank you.
I appreciate that. I very much appreciate it when you try to give me intuition, and I know that that's dangerous, especially trying to give me intuition, but I do appreciate it.
It's good. I like interactive seminars rather than just.
Let's all go back to the institute and have some coffee, or in my case, have some more coffee.
To me, it's interesting that somehow you have quite different methods here for k equal to 3 than from k equal to 2, because k equal to 2 you start with the endpoint, but here somehow start with a point in the middle, and then you don't know which point is, so therefore you have to look at all possible starting points and then use something optimization at the end, as you said.
Well, this gave us the intuition, but for the proofs, we still started from the endpoints and then grew these balls and then
Yeah.
looked at when do they intersect.
Okay.